Welcome to second session on deadlocks. Till now, what we have done, we've seen deadlock prevention. While talking about deadlock prevention, we had talked about the conditions which are necessary for occurrence of the deadlock. So we've seen that there are four conditions which are required for a deadlock to occur, and we tried looking at a prevention approach where what we have tried to do is we have tried to see to it that one of those four conditions can be eliminated, and we found that attempt to eliminate the conditions are not always possible. Therefore, deadlocks, the one conclusion which we can have is deadlocks cannot be prevented. So, having known that deadlock cannot be prevented, then there are other approaches. We would try to focus that if we can avoid the deadlock from occurrence, and we would notice it shortly that for avoiding the deadlock, there are certain additional information which is going to be required to be known a priori. We will find out what it is. And having talked about deadlock avoidance, we will also, so the third approach which we can do is that we can allow the deadlock to occur in the system and then detect the deadlock, and after having detected the deadlock, devise a mechanism to recover from the deadlock. So, we will try to in this session we will try to focus on these two aspects of deadlock handling, avoidance and detection and recovery. So, let us begin with the avoidance first. So, for as I just mentioned, that for us to be able to avoid the deadlock, we would find that we would notice that there are certain requirements, certain additional information which are required to be known a priori. So, one of the simplest thing which is required to be known is a maximum number of resources of each type that a process may need. So, we call this as a need. If we would need to know that what is the need of a process, then only we can probably have an algorithm which will help us in avoiding the deadlock. And in case of a deadlock avoidance algorithm, what it tries to do is it dynamically tries to determine the resource allocation state. And what it tries to do is that somehow it tries to work in a manner that circular wait does not occur. So, so essentially it is important that we know we need to know the resource allocation state. And when we talk about a resource allocation state, this would have this state can be characterized by the number of available resources in the system, number of allocated resources, and if it is possible for us to know the maximum requirement of a process. So, if we know that if these three informations are the main information, these is it, which if they are known, then we find that probably some algorithm can be worked out which can avoid the deadlock from occurrence. So for us to work out the algorithm, let us I would try to define something known as a safe state. So what we need to do is whenever a process requests an available resource from the system, system needs to decide that if suppose the resource is allocated immediately, whether it would lead to, it will remain in a safe state or it would lead to deadlock. So what we need to do is we need to define a notion of a safe state. We will see that how the safe state is defined. So we say that a state is a safe if system can allocate resources to each process, that is it can meet all the requirement of a processes, and it can still avoid the deadlock. So if that can be achieved, then we say that a system is in safe state. Broadly this is how we would say that we would find that at a given instance of a time, a process may make a request. Now the algorithm should check that if suppose such a request is granted, then will it lead to a system state where system can be in a safe state. If system can be in a safe state, then that allocation request can be granted, otherwise the allocation request may not be granted. So we say that a system, we would work out with some kind of algorithm where we would say that a system algorithm for finding out a system, so whether the system is in safe state or not, and we would see that if the system exists in a safe state, then we are going to have a sequence that we call as a safe sequence, and safe sequence of all the processes. So safe sequence essentially is an indicative of a safe sequence is a safe sequence is a indicative of processes, the order in which the processes can be executed, so that the maximum requirement of each process is met by the release of the resources from the its predecessor process. So let us see that here we try to indicate that what a sequence means. So we say that we have a sequence, say a sequence of a P1, P2, Pn. We say it is a safe sequence if for every Pi the resource that Pi request can be satisfied by currently available resources plus resources held by all the Pj where j is less than I. So meaning to say that if suppose we talk here, so we say that if suppose the process P2's request can be met by the available resources plus the resources which are released by P1, because in this case we are assuming that P1 would have executed. This is a sequence, so it means that P1 would first execute, then P2 would execute, then Pn would execute. So if we are talking about a P2, before P2 P1 would have executed, and that essentially means that it would have released the resources which it had held. So the resources released by P1 plus the available resources, if they meet the requirement of a P2, then P2 can execute, and so on. So this is what we call as a this sequence. So a sequence generated in this manner is named as a safe sequence. And we find that we say that Pi we say that when Pj is finished, Pi can obtain the needed resources, execute and return allocated resources and terminate. So in this manner, successively every process would get a chance and would be able to execute without causing a deadlock. So there are a few basic facts which we need to think about the safe state. So we say that if a system is in safe state, it guarantees there would be no deadlock. If a system is in unsafe state, it is indicative of possibility of a deadlock. it doesn't always necessarily mean that if a system is in unsafe state, it will necessarily enter into a deadlock, because it may happen that a particular process which has made a request for some resource and which has led to unsafe state, it may just happen that the processes may not require any more resources and they may simply exit from the system, so releasing all the resources, and therefore the system may once again enter into a safe state. So the avoidance scheme essentially tries to ensure that system will never enter in an unsafe state. So that is what the any avoidance scheme would try to achieve. So diagrammatically we can say that we define the state of a system as a universal set, and we say that some part of it is a safe and another part of it is unsafe, and inside the unsafe state we say that certain things, certain set of states can lead to a deadlock, certain specific things can lead to a deadlock. So not all the unsafe sequences, all unsafe states are necessarily in a deadlock. Out of some unsafe state, there are subset of states which lead to a complete deadlock. Let us see a very simple example to find out that if suppose we can, just by looking at a system, can we say that a system is in safe state or not. Later on we will work out a detailed algorithm for doing it, but here what I have done is I have presented a very simple case. In this particular example we have three processes, P0, namely P0, P1, P2, and we have a total number of 12 resources available in the system, and at a given point of a time we are saying that P0 has been allocated 5 resources, P1 has been allocated 2 resources, and P2 has been allocated 2 resources. So out of total we find that there are 9 resources which has been allocated, and let us see that along with the allocation there is another information which we have, and that is say maximum needs. So we say that a process P0 maximally may need 10 resources, process P1 could need 4 resources, and process P2 could need 9 resources. So this is a maximum requirement, and we should understand that somehow once the process has it has been found out what is the maximum requirement of a process, then these processes are not going to request more than their maximum requirement. So assuming that now if we see that the current situation, so in a current snapshot we find that 9 resources are allocated, and there are total number of resources which were there in a system 12. So out of 12, 9 have been allocated. So the remaining, there are only 3 resources which are left out. So now with the 3 resource, if we try to look at a P0, we know that P0 could actually make a request for 5 more resources. So if we allocate these 3 resources to P0, then we find that rest all the processes will get into a deadlock, because after having allocated 3 resources, now P0 will have 8 resources, and it could further make a request for another resource, and P1 and P2 also may make a request. So the these processes will get into a deadlock. So we find that P0 cannot be allocated the resource. Now let us see P1. So P1 has an allocation of 2 and maximum need was 4. So now remaining requirement is 4 minus 2, remaining need, I can say remaining need could be 4 minus 2. So, it may require 2. So, we can say that since we have a 3 resources, so we say that we would allocate 2 resources to P1 whatever it requires. So, P1 will actually get 4 resources, and once it is allocated 4 resources, it will terminate, it will execute and terminate. So that is the reason that here you can see that I have in a sequence, safe sequence which we are deciding, we have marked P1, that is we are saying that P1 should be executed first. And now when P1 would execute, so what P1 would try to do is, P1 had if suppose P1 executes, so P1 was allocated 2 resources, when P1 executes and complete, it will release its 2 resources. So now the remaining number of resources which we are going to have is going to be 5. There were 3 earlier resources and 2 new resources which are going to be there. So the total resources now becomes 5. Now we know that we can allocate 5 resources to a process P0. We know here that P2 cannot be started because P2 requires 7 resources, whereas your available resources are 5. So P2 cannot be the next process. So we go back, we check for a P0, and we find incidentally that P0 requirement can be met because availability is 5. You have a 5 available resources, and P0 may make a request for a 5. So as a consequence, P0 is the next process which should execute. When the P0 is completing, then now it will release all the 10 resources. So now with the help of those 10 resources, P2 requirement can always be met. So we can very clearly see that we can work out a sequence which will, if the processes are executed in that sequence, then we find that deadlock would not occur, and such a sequence is known as a safe sequence. Let us there are various approaches for doing a deadlock avoidance. One of the approach is based on a resource allocation graph. We will see that how it works out, and then there is we will also see that a resource allocation graph is a kind of a thing which works with the resources where we have a single instance of resources. If we have a more than one instance of a resources, then this resource allocation graph algorithm does not work. So we define different kind of edges. So we have a first kind of edge that we call as a claim edge. So we say that if ith process is trying, or ith process is trying to indicate that it may request a resource Rj. So this is indicated as a claim, and then this is an intent. Please understand there is we are defining a various things. One is a claim edge. So claim is a kind of an intent that a process Pi intend to claim a resource, and whenever process Pi tries to claim the resource, what it is tries to get the resource, then what it is going to do is it is going to make a request. So then the claim edge would get converted to what we call as a request edge. So whenever the process would make a request, formal request, then the claim edge would get converted to request edge. And once the resource is released by a process, or resource is allocated to the process, then it becomes what we call as a assignment. Then when the resource is held by the process, then we represent it through what we call as a assignment edge, and whenever the process releases the resource, the assignment edge gets converted to a claim edge. And we should also understand the algorithm works where it is assumed that a resource must be claimed a priori in the system. So, in this algorithm will only work when all the processes which are there in the system, whatever resources they need to acquire, they must claim it first, and then through a request, these edges would get converted to a request, and through allocation the request edges would get converted to assignment, and through release operation assignment edges would get converted to claim edges. So, let us look at a very simple graph. This particular graph is indicative of that process P2 is making a request for R1. This is indicated with the solid line, and resource R1 has been allocated to a P1. So, there is an edge. This edge is assignment edge. We see here that a process P1 is connect P1 and P2, both of them are connected to a resource R2 through a dashed line. This is essentially a meaning that P1 and P2 might stake claim for a resource R2. Now, in the next instance, it may happen that P2 made a request, and once the request was made, the resource was allocated. So, P2 made a request, so it got converted into a request edge, and since the resource was available, the resource was given to a P2. So it is this edge gets converted to a assignment edge. P1 has yet not made a request. So, P1 is connected to a R2 through a claim edge. Now in this case, we can very clearly see that if suppose P1 makes a request for a R2 resource, and this request, this claim edge is converted to a request edge, then we find that there is a cycle which exists, and because of a cycle we can very clearly see that there is going to be a deadlock. So in this case, this resource allocation graph, what we can do that whenever a request comes, we would try to see that whether grant of that particular resource will lead to a cycle in the resource allocation graph. If grant of request would lead to a cycle in a resource allocation graph, then in that case what we shall not convert claim edge to the request, and we shall not do it, and therefore we can very easily avoid the deadlock. But please notice one thing, that this kind of approach is only suited for the case where we have a single instances of resources. For a multiple instances, if suppose we have a 2 instances of R2 resource, then we can see that whenever if suppose there were 2 instances, so one instance is allocated to P2, and if P1 makes a request, whenever even if it gets converted to a request edge, we can very clearly see that second resource can be allocated to a P1, and both of them can. So actually P1 can execute whatever it wanted, it has got everything and it can execute. So we can very clearly see that in this case, when we have multiple instances of same resources, this approach, resource allocation graph approach, cannot be applied for deadlock avoidance. So we need to find out, we need to find out a approach which will be valid for multiple instances of resources as well. So there is an algorithm which we'll try to see, and see which handles the scenario where we have multiple instances of resources, and this algorithm is known as a Banker's algorithm. The characteristic of a Banker's algorithm, Banker algorithm is characterized by multiple instances of resources, and in this case, as we saw that each process must require a claim, in a previous resource allocation graph we had seen that each process must make a priori claim for the resources. So same thing is required here. So we say that every process must a priori give its maximum claim, and then whenever a process requests a resource, it may have to wait. They complete the algorithm requires that if the resources are not currently available, the requesting process would need to wait. And when a process gets all its resources, then it is assumed that the process would execute, complete its task, and after completing its task, it will return all the required resources in finite amount of time. So meaning to say that a process would get the resources, and on the completion of a work, it will faithfully return or release all the resources. So for this, for a Banker's algorithm, we going to show that there are number of data structures which are required. So we are assuming here that let us assume that we have a n number of processes and m number of resources, where different types of resources. So we define something known as available, which we say is going to be a vector of a length m. So if length m, so we say available of j equals to k, it essentially means that there are k instances of resource type rj available in the system. So available vector is a vector which is indicative of the fact that how many resources are currently available, how many instances of resources of each type are available in the system at a given point of time. Then we have another matrix. We define it as a max, which is a n cross m matrix, where n is a number of processes and m is a number of resources. So max I comma j, if we say that a max I comma j equals to k, then this is essentially indicative of that ith process may request at most k instances of jth resource. This is what it will mean. So max is defined in this way. Another matrix which is similar to the previous matrix, which is allocation matrix. So in the same way we can interpret this, that if allocation I comma j equals to k, then we can say that p ith process is currently allocated k instances of jth resource. So that is a allocation. So these are the three important data structures which we require. In addition to this, what we do is we compute something known as a need matrix. From a max and a allocation, we compute the need. So need matrix is defined as the need matrix is a matrix which will define what is the remaining need of a process is. So we find that we have need matrix, and this need matrix is again similar to the previous matrices, is again a n cross m matrix, and in this case need I comma j equals to k essentially means that ith process would need k more instances of rj resources to complete its task, and it can be computed by subtracting the maximum ij minus allocation ij. So maximum it can be simply obtained by subtracting a matrix max allocation from the max matrix. So need can be obtained in that manner. Let us look at a safety algorithm, how it works. So for us to define the algorithm, what we do, we define two more vectors working so one vector we call as a work and another vector we call as a finish vector. The work vector is of length m and finish vector is of length n. So in the beginning what we do is work vector we initialize with the availability. So available, please remember that in a previous slide we had said that availability is a vector which defines the availability of number of instances of each available resource in the system. So to begin with, what we do, we define work equals to availability, and to begin with, since we would need to find out a safe sequence. So we saying that in the beginning all the processes we have not tested, so we are defining a finish vector which is of a length n equals to a false for all i's. So what we do is that we begin so at a next step what we do, that we find out we find an index I such that both the conditions are true, that is a condition A and B here, that is a finish I is false and need I is less than the work, that is a need is the current need of ith process is less than the availability. So if the current need of a process pi is less than the availability, meaning to say the available resources, then its requirement can be met, right. So what we need to do is we need to find out an index I, and for that I these two conditions must be true. So let us say that if such a thing is found out, so if suppose such a condition, so at a statement number 3 I am saying that if no such I exists, then go to step number 4. So let us see that why such a thing would occur, like what are the various possibilities when such a thing would happen. So if suppose the condition 1, that finish I is equal to true, for all I it is true, it means that all processes have been checked and everything is true. So that is the one case when we would need to go for. So since all processes have been checked, we don't need actually the second condition, since there is no process for which the need can be checked. So that is the one case. The second case is that what happens, that we have I equals to false, but what happens, that need is not less than work. We have a I for which is false, and we find that the current available need is not less than the availability. So in this case also we find that we may have a situation where such a thing could arise. So in that case also we will come to the step number 4. So this is a clear cut case that there is an I which is a false and need is and your need is not need is greater than the work. That means that we are in deadlock, the system is in unsafe state. But let us assume that these two conditions are satisfied. So when these two conditions are satisfied, we come to the step number 3, where what we do, so the assumption is that since need for the ith process can be met by the availability, this essentially means that the ith process would get the resources, and after working, after finishing, what it is going to do is it is going to release all the resources which it was holding. So that would mean that whatever allocation was there is going to be released by the ith process. So that is what we are trying to indicate, that ith process gets the resource, and after getting the resource, what it does, the work is changed. Now we can see that work is written as a work equals to work plus allocation I, meaning to say all the resources which were allocated to the ith process, they are added to the availability vector. And since the process has completed, ith process has completed, its finished value is marked as a true, and then we return back to the step 2. So this we can very clearly see that if we execute this particular algorithm, at the end there are two conditions which might occur, that is all finish I is equal to true. If all finish I is equal to true, then we say that the system is in safe state and we have a safe sequence. If we find that there are set of processes, there are a set of processes for which the finish I is not true, false, then we know that those processes are in deadlock. So so this is how the safety algorithm functions. Let us take a very simple example. To illustrate the fact that how do we say a system is in safe state or not, and how do we determine a safe sequence. So this is a case where I am saying that we have claim matrix. So this is a maximum claim. So this essentially says that P1 would require maximum of 3 instances of resource type R1, 2 instances of resource type R2, and 2 instances of resource type R3. In same way, we can say that a P2 requires 6 instances of resource type R1, 1 instance of resource type R2, and 3 instances of resource type R3. So this is how the claim matrix is interpreted. In the beginning, we trying to indicate a allocation matrix. So in this case, it is indicative that a process P1 has been allocated 1 instance of a resource R1, no instance of resource R2, no instance of resource R3. Similarly, P2 has been allocated 6 instances of resource R1, 2 instance and 1 instance of R2 and 2 instance of R3. P3 has been allocated 2 instance of R1, 1 of R2 and 1 of R3, and P4 is allocated 2 instances of R3, and it has not been allocated any instances of R1 and R2 type. So this is the allocation matrix, and at this point of time we say that the available vector is 1 1, that is there is a 1 0 1 1, meaning to say we have no resources of resource type R1 available in the system, all are allocated. So we can actually find out if we sum total the allocation and the available, that gives me the complete number of resources. So we can see that we have a 1 6 2, that is 9, and 0, that means that 9, there are 9 instances of resource type R1 in the system, and that is what I am saying, that my resource vector is here, that we have initial, like when the resources are not allocated, we have a 9 resources of R1, we have a 3 resources of type R2, and we have 6 resources of type R3. So here we can see that we have a 2 1 2, that is a 5 plus 1 6, and 1 1, and we have a 1, so that is 3. So we have a available vector. So this is a something which we are saying that we should know, that claim matrix, we are saying that we must know what is the maximum number of resources each processes are going to use. So there should be some mechanism by the processes for the processes to specify the maximum requirement, and we know it very well that such kind of a thing is not going to be possible, because the processes usually, the way programs are written, we find that one requires, one incrementally takes the claim for various resources. So this is one of the problem with the avoidance algorithm, but let us just look at it, that how the whole algorithm works. So we have a claim and we have a allocation. So from this, what we can do is, what we can derive the need matrix. So here I have computed and shown the need matrix. So we can see that claim minus allocation. So 3 minus 1, that is 2 here, then 2 minus 0, 2 here, 2 minus 0, 2 here, then 6 minus 6, 0 here, 1 minus 1, 0 here, 3 minus 2, 1 here. So we in same way, it's a very simple mathematics. We just subtract element by element from the matrix to get the need matrix. So we can see that from this we can, this is what the example is. So now what we need to do is, from this we would need to find out that if we have a safe sequence, or if the system is in safe state. So the very first thing which is needed to be known is if the system is in safe state or not. So we've seen that from here we can very clearly analyze that if the system is in safe state or not. So now let us see that what we have. We find that we have a available vector which is a 0 1 1, and so we try to look for the need which need can be met. So we find that the process P2's need can be met by this. We cannot, the P1's need cannot be met because P1 requires 2 2 2, P2 requires 0 0 1s, and so the need is less than availability. In case of a P3, need is greater than availability. In case of a P4, again need is greater than availability. So we can say that P2's need can be met. So what we can do, that we can now do the release operation for a P2. So if you just look back the algorithm which was there, that we are at this stage, we say work equals to work plus allocation I. So essentially what I am getting is my availability vector will get modified and I will get a allocation. So I'll get I'll add the allocation of ith, that is I would add the resources held by the P2 process to my work. So work is initialized to availability. So in the beginning work is 0 1 1. When P2 releases, so P2 will release 6 1 2. So now this will become 6 2 3. So your availability vector will become 6 2 3. So now one should check that if we can now meet the requirement of some process or not. So we find that P3's request also can be met, because P3 is only requiring 103, and this is a this will be a 6 2 3. So P3's requirement can be met. So now when P3 completes, P3 will release 2 resources. So now my this value will become 6 plus 2 8, and R2 will become 3, and R3 will become 4. So, I have a 8 3 4. We find my P4 would be met, and once P4 is executed, P4 would release resources. So, after that what happens, that all the resources would be made available and P1 can execute. So, we can very clearly see that we have several safe sequences in this case. We can say that one of the sequence would be P2, P3, P4, P1, and there can be many more sequences. So it at a given instance of a time, we can find out whether the system is in safe state or not. So, now let us look at how the algorithm would work, resource request algorithm for ith process. So we say that request I is equal to request vector for a process I. So, here we are defining a vector. Please note that when we write a request I, it is a vector actually. It is a vector of m elements, and this is request I is corresponding to request by the process ith process. So, request I of j equals to k. This essentially means that the process I wants k instances of resource type j. So in this case, we are comparing, we are saying that the algorithm works, the resource request algorithm for process works in this way. Since we are looking at avoidance, so what we try to do is that we try to look at the resources by the process. If the resources request of a resource, grant of a resource is going to lead to a unsafe state, then what we do, we don't allocate the resource. Otherwise we grant the request. So we are checking here. So we begin with checking if request I is less than need I, then go to step 2. That is, need is a maximum requirement, maximum unmet requirement. So what essentially this step is trying to do is, it is trying to check that if the process, ith process is making a request which is less than the maximum unmet requirement. If suppose the request I is greater than the need I, this essentially means that the ith process is trying to make a request which is more than its maximum claim, and in that case what we need to do is we need to raise some kind of alarm. That is, we should say that it can because the process initially said that it only wants 2 resources, and now it is trying to ask for a third resource as well. So error condition occurs. So that is one condition. So we would assume that it would never happen that dynamically the process request is going to become greater than its need, is going to change. So let's assume that this is going to be a less, then we going to step number 2. Now what we do is we check that if request is less than the availability. Let's say that if request is greater than the availability, so this essentially means that the process is trying to make a request for a resources, and those resources are not available in the system at present. They are probably held by some other processes. So as a consequence, the very logical thing would be that these processes, the process should wait. So in case the request I is less than the availability, then in case request I is greater than the availability, then in that case the ith process must wait must wait till the time the resources gets released from the other processes. And in case request I is less than the availability, then the algorithm works in this way, that what it tries to do is that it will pretend to allocate the requested resource to ith process. So what it does, it tries to say that available equals to available minus request I, because this is a new request. So we are saying that we are pretending that as if the request is getting granted. So when we grant the request, that would mean that availability will reduce and allocation would increase. So we say that so availability reduces and allocation increases. Now what we do, we check now need I is equal to need I minus request. Now we recompute the matrix. So we get the modified need matrix. So essentially what we are saying is that whenever a request comes, we pretend if the request is granted, if it is if it can be met by the current availability, and then we obtain the new state, and from that new state we try to find out if the system is in safe state. If the system is in safe state, then it is all right, then it is okay. If the system is in unsafe state, then we do not grant the resource. So this is how the resource request algorithm works. And we can very clearly see that by this means what we are doing is we are trying to avoid occurrence of an unsafe state. We are trying to say that a system would not be able to enter in the unsafe state. So here we indicate, we take a very simple process and we try to show that how the whole thing would work. Simple example, this is also listed in the book. So we see here that we have 5 processes P0 to P4, and there are 3 resource type, we calling them A, B, C, and there are 10 instances of resource type A, 5 instances of resource type B, and 7 instances of resource type C. So this is what and at a given point of time we are saying that max is this and the allocation is this. So and availability is this. So current availability. So this is a snapshot of a process at some instance of time t0. Now what we need to do is we need to find out whether the system is in safe state or not. So from it, so from these given values, what we can do, we can find out a need matrix, and you can check it out. You can check it out that with this what would be the safe sequence. So one of the safe sequence which we have written here is P1, P3, P4, P2, P0. Let us just work out a 1 or 2 steps and see that how it works. So we find that we have a availability that is 3, 3, 2. So let us check that if P0's need can be met. So we find that P0's need cannot be met because need is greater than the availability. So when we say, please note one thing, that this comparison less than greater than is a vector comparison, where what we are doing is we are saying 7 is greater than 3, 4 is greater than 3, and 3 is greater than 2. So if we say that a P0 is less than, or a Pi is less than availability, that essentially means that all the 3 values here are less than corresponding 3 values here. Then only it is less, otherwise the condition gets violated. So in this case we know that P0 cannot start because P0 the need is 743. Then we find P1. So P1 is 1, 2, 2. So we very clearly see that 1, 2, 2 is less than 3, 3, 2. So we say that process P1 can be the potential process which can be started. So we write it here, right? And we find from here that once a P1 executes, so the allocation, that is a 2 0 0. So this process will become 5 3 2. 5 3 2. Let's see that P2 cannot be started because P2 requires 9 instances of resource type A, whereas what we have a 5 resources only. So now we come to next one, we say P3, and we find P3 has a 2 2 2. So you can very clearly see that how the safe sequence is determined. So this is how we would say that a safe sequence. This is how we would check, and we would say that the system is in safe state. So the given system is currently at a safe state. Just to indicate an example, I am not going to demonstrate how it would work. Since I have described the algorithm, what you need to do is you need to just work it out. So I am leaving two things to you here. So I am saying that let us assume that the process P1 makes a request for a 1, 0, 2, meaning to say that it makes a request for a 1 instance of a resource type A and 2 instance of a resource type C. P1. So we should see that what happens here. So we find that what we have is we have a 1 0 2 which is a less than availability. So 3 3 2 is true. So here we are saying that we would check for a process P1 its request can be granted from the whether it can be granted from available resources or not. So we find that if we just refer the previous example we said that we have a availability of a 3 3 2. So process P0 is P1 is trying to make a request which is for 1 0 2. So when P1 tries to make a request for a 1 0 2 which can be met from a 3 3 2, so my need matrix and my allocation matrix both will get modified. So this is what I get, a modified matrix. So after granting, so after pretending to grant the request, this is the matrix which I would get. And once I get this matrix, then what I need to do is I need to check out whether this snapshot of a system would give me a safe sequence. If I get a safe sequence, then in that case I would grant the request, else I would not grant the request. So incidentally, what happens, when you work out this algorithm, you would find that there exists a safe sequence, that is a P1, P3, P4, P0, P2, and therefore the request can be granted. And I leave 2 exercises for you, that let's assume that if request by P4 can be granted, and if request by P0 can be individually granted, you can just check up one after the other. You try satisfying, after solving this, you try satisfying this and try satisfying this. You would find that one of them would lead to an unsafe state, therefore it can be prevented. So we have seen an algorithm for avoiding the deadlock, but one of the biggest issue there is knowing the maximum amount of resource requirement by each processes. So this requires that each process a priori right in the beginning of a program is specify the total number of a resource requirement. We find it is going to put a quite extraordinary burden on each of the programmer, and many a times it would happen that the programmers would not even know that what is the total number of all kind of resources which their program is going to require. and moreover, secondly, it would also lead to a kind of suboptimal utilization of resources, because a process may actually claim a lot of resources, but it may not use any of the resources. So and computationally also we would find that this algorithm, executing this algorithm for a large set of processes is going to be really cumbersome. So we say that deadlock avoidance algorithm is also, actually we don't find deadlock avoidance algorithm being used in any system. In fact, neither a prevention nor deadlock avoidance. And to be very frank with you, in most of the system, actually we don't do anything for the deadlock, but then it is an important aspect which we need to study about and be aware that such a condition occurs. And who knows, tomorrow some new mechanism or new developments may result where a deadlock can actually be eliminated. But nonetheless, let us look at a last approach, which is where we are saying that a deadlock detection. So in this case, what we are saying is, we are saying that allow system to enter into a deadlock state and then detect the deadlock. So we need to have an algorithm which is a detection algorithm, and having detected the processes which are in deadlock, then we should devise a recovery mechanism. So let us just try to see that how the whole thing would work out. So one of the thing which we have seen in an earlier case was a resource allocation, the algorithm which was based on a resource allocation graph. So we try to use the same resource allocation graph, and using that we try to devise an algorithm. So and as we know that resource allocation graph was only valid for a single instances of resources. So this approach is also going to be, the suggested approach is also going to be only valid for single instances of resources. So let us see that what we do here is we try to maintain something known as a what we call as a wait for graph. We will see that what it is. So in case of a resource allocation graph, we said that we have two different kind of vertices. We said that we have a resource and a process as a vertices, and then we had said that we have a various edges. In this case, what we are doing is we are going to have a nodes only, nodes are going to be there which are only going to be a processes, and if we have a process and then processes and then there are edges, so we say that a PI is waiting for a PJ. So directed edge, PI directed edge to the PJ, then that edge is indicative of that PI is waiting for PJ. That is PJ is holding some resource which PI is requesting. This is what it would essentially means, that PI is waiting for PJ. So and what we try to do is, so we maintain a graph and we try to search a cycle in the graph. If the cycle in the graph is found, that is indicative that there is a deadlock, and then we try to break the deadlock. So let us just take a very simple example of a resource allocation graph and convert that into a wait for graph. So in this case we can see very clearly that there is a process P1 which is requesting for a resource R1 which is allocated to a resource which is allocated to a process P2. So what we are saying is that P1 is waiting for P2 because P2 is holding a resource R1 and P1 is waiting for that. So we eliminate this and directly connect P1 to P2. So P1 to P2. Similarly, let us see that we have a P2 is making a request for a R3 which is held by P3. So we can say P2 is waiting for P3. So we draw a line between P2 and P3. In same way, we can say that P3 is holding a resource, is making a request for a resource type R5, which is held by P4. So P3 is waiting for P4. Similarly, we can say that P4 is requesting R2, which is held by R1. So P4 is waiting for R1. So in this way, we can very clearly construct we can construct a graph of this kind. And then, having constructed a graph of this kind, now what we can do is we can try to see that if there is a cycle. If there is a cycle in the graph, then we can say that there exists a deadlock. If there is no cycle in the graph, then we say there does not exist a graph. We can we can see it clearly that this particular approach would purely work for the case when we have a single instances of resources. And this algorithm, the thing is that whenever a new request has to be made, the algorithm has to be there is wait for graph has to be generated, and the one has to check for the cycle and one has to find out. So let us try to look at that. Can such a thing be? Can we propose something where several instances of resources are involved? So here we try to propose an algorithm which will allow us to handle the several instances of resources. So we define a available factor, which is the same as a previous case. So available is a vector of length m, indicating the number of available resources of each type. And we know that at any given point of a time, the allocation is going to be there. The system has a total number of resources, that information is there. Then allocation, that whatever resources are allocated to each, so system would keep track of. And the current request, that information is also available. So this approach, unlike the previous approach where we were talking about deadlock avoidance, where we said that a maximum claim is needed to be known, what we are doing is this algorithm is only based on the information which is available in the system. So we say that we at any given instance of a time, availability, allocation and request, these are the three things which are always going to be known. So the detection algorithm works something like this. So similar to the previous case, what we are saying here is we are saying that we have we define two vectors, work and finish, where work is of length m and n is and finish is of length n. They are serving the same purpose. So to begin with, what we do, we initialize work equals to availability, and then what we do that we initialize finish I equals to false if allocation I is not equal to 0. We should understand why we are doing it, because if a particular process has not been allocated a resource, any resource, then this process cannot be a part of a deadlock. So that's the reason that in this case what we are saying that if the allocation I is equal to 0, then in that case what we are doing, we would say finish I equals to true, because it cannot be a part of this thing. So we initialize it to a false, only selected. So this is how my initialization would take place. Then the rest of the approach you find is going to be the same as previous case. So what we are saying is we would check, find an index I such that both finish I is equal to false. See, this algorithm is more or less similar to our safety algorithm. So we say that finish I is equal to false and request I is less than the work. So your request can be met by the availability. The request by the process I can be met by the availability. If no such if suppose request of process I is not less than availability, then we are going at a step number 4. And if such a thing, if these two statements are satisfied, then what is happening, that we come to the step number 3, where we say work equals to work plus allocation and finish I equals to true, and we go back. So in this way we try to finalize this algorithm is executed. And finally, at a step number 4, you can see that what we are doing is we are trying to say that if finish I is equal to false for a sum I. So if we find that at the end of executing these algorithms, if we find that there is a sum I for which the finish I is equal to false, then it essentially indicates that those processes are in deadlock state. This is indicative that the system is in deadlock, and the set of processes for which finish I is equal to false, they are involved in deadlock. So we once again we can take an example. We can say that we have a 5 processes P0 to P4, 3 resources, and this is what it is. And we can very clearly see that this is a snapshot. So at this point of a time, we can say that whether the system is in safe state or not, and we can figure out the safe sequence, and we find that finish I will result into a true for all I. So this is an indication that the system is not in deadlock. We can see examples where actually the system would be into a deadlock. This is an example. What one can do is that you can check that if suppose P2 requests an additional instance of type C. So we would find that eventually what happened, that system would get into a deadlock, and the deadlock would start occurring. So now we've seen that how to detect a deadlock when the system is in deadlock state, how to detect that whether it is in deadlock or not. Now the question arises that when and how often this deadlock algorithm should be invoked in the system, and we do not know, actually we do not know that how often the deadlock can occur in the system. And we should also understand that even if we detect the deadlock, so there are issues. The number one issue, that what is the periodicity, or how often the deadlock is going to be, deadlock detection algorithm is going to be done. So one approach could be that for every request, whenever a request is made and request cannot be granted, so at that point of a time what we should do is we should try to run the deadlock algorithm and see that if deadlock has already occurred or what, or we can have some kind of a periodicity. Or another approach could be that whenever we know that whenever the deadlock is going to occur, what would happen, that it will actually lead to the degradation of a system performance. So for that reason, that what can be done is that we can even fix some kind of threshold limit on a CPU utilization, and we say that if the CPU utilization drops down below certain percentage, then the detection algorithm can be run. Please also understand one thing, that having run the detection algorithm, now let us say that we know that what is which is the process which are there in the deadlock. Now what do we do with them? So because we have detected the deadlock, there is a process there are set of processes which are in deadlock. So now what can be done? Deadlock is, we should understand why deadlock has occurred. Deadlock has occurred for the reason that there are resources which are held by some process, and another process is waiting for that resource in a cyclical manner. Now, this is condition which will remain there if somehow the cycle is not broken. And breaking the cycle essentially means that what we would need to do is we would need to forcibly make certain process to release the resource. That essentially means that these processes would need to be aborted or terminated or preempted, or the resources are to be preempted from the processes. So one approach could be that I abort to one process at a time until the deadlock cycle is eliminated. So what we can do is we abort one process. So when we abort one process, what would happen? That this process would release some resources. Now with that additional set of resources which are released, we try to see that whether the deadlock will get broken. We try to run the algorithm, detection algorithm, and if the abort of a process, with the abort of a given one process, if the deadlock can be eliminated, well and good. If it cannot, then choose another process and keep deleting, keep aborting process one by one till the time a deadlock is eliminated. See, aborting a process is going to be problematic, in the sense that the processes would have carried out some work, and when we are trying to abort, probably they may even require some kind of a rollback. So that is something which is to be taken care of. That becomes a problem. And then when we are trying to abort the processes, then again question arises that which particular process should be chosen for aborting. So should we decide based on the priority of a process, or should one decide based on how long a process has been there in the system? So one approach could be that the process which has been there for the longest period of time may not be aborted, because it might have carried out a lot of work and might have used a lot of resources, so it need not be aborted. The other approach is just the opposite approach, where it is assumed that if a particular process has been executing for a very long period of time, then probably this is the process which has been holding a lot of resources, and if it is eliminated, then all the resources would get eliminated and lot of other processes can complete. So there are various variety of possibilities which one can use for aborting a process. So when we are looking at after detecting the deadlock by aborting the process, what we are trying to achieve is we are trying to recover from the deadlock, and there are issues in terms of that choice of a victim itself. And another approach could be that what we do is that we try to do a resource preemption. We don't abort the process, but we try to do a resource preemption, meaning to say that forcibly somehow we try to get the resource preempted from the working device. So in this case also would involve selecting a victim, where we would select a victim, and from that victim what we'll do is we'll try to preempt the resources. And in such a case, since the process is not being aborted, then since we are preempting the resource, then this would require some kind of a rollback, that is a return to some kind of a safe state and restart that process from that state. and we can very clearly see that if such a thing is going to be there, so it may happen that every time same process could get selected as a victim process, where its resources are going to get preempted, and this could lead to what we call as a starvation. So and so starvation is a possibility, that whenever we would try to select a victim, either in a case of aborting the process or even for preempting the resources, the starvation is a possibility. So I would just want to conclude here that we've seen the three approaches. One was a prevention. We found that prevention cannot be applied. Then we tried finding out a mechanism of avoidance. Again, for avoidance, we have seen that we require certain informations which are not a priori available in the system. So avoidance also cannot be applied. Finally, we have seen a mechanism where we said that processes could be allowed to get into the deadlock and then look for some kind of a recovery. So there are pretty good algorithms which will be able to find out, detect the deadlock, but then the issue arises in terms of a periodicity of running these algorithms, and the most importantly the issue arises with that selecting a victim process to break the deadlock. So currently we find that none of these approaches are used, and in most of the general system the deadlocks are allowed to occur. Once in a while the deadlock does occur, and then at that point of a time, what system administrator does as system administrator, when it observes that somehow the processes, the system performance is going down tremendously, then what it tries to do is it tries to find out manually set of processes which are hogging a lot of resources and tries to kill them, or in a worst case even it may happen that one may need to press the reset button to recover from the deadlock. Thanks.